Namaste.
Namaste, Padma ma'am.
Namaste, Radha ma'am.
Great to have you today. Let's take up some changes, physical and chemical changes. Let's understand them better.
Right?
We all know what physical changes are. Physical changes are those, like example is dissolution of a salt in water. It's a physical change. As simple as breaking of a metal. We have magnesium ribbon here. Ma'am is breaking a piece of the magnesium ribbon. This is magnesium and alkaline earth metal, a piece of it. It's a metal which can be easily broken. Unlike other metals which cannot be broken, this can be taken and sliced easily. These are called magnesium ribbons. Now this breaking of magnesium ribbon is a physical change. Ma'am, can you tell us a few more examples of physical changes?
Yes, ma'am. When we heat water or when water lies wherever it is in the rivers, ponds, lakes, seas, they get evaporated.
Right.
They change from water, liquid state to the gaseous state. That is an example of a physical change. And when the water vapor goes up, when it cools in the higher climes of the atmosphere, it cools down and it condenses and forms water droplets again and comes down as rain. That is again a physical change that is happening in nature.
Yes. Ma'am, if I consider tearing off a paper, could it be considered as a physical change?
Definitely, because there is no new substance formed there. But however, you will not be able to get the paper in the same form. Paper continues to remain as paper. There is nothing that has changed chemically in that paper. So that is also a physical change, but an irreversible physical change.
Right, ma'am. So water from liquid state going up to vapor state, where the molecules of water in the liquid state just change its states from that where it is with that energy, gets higher kinetic energy and moves up to the vapor state. Is that also a physical change according to you?
Yes, ma'am. There the water molecules move apart from each other. From the liquid state, they move on to the gaseous state or the vapor state.
Right.
There is nothing chemically that changes in it.
Yeah.
So that is also
a physical change.
Right.
Now that we have got a clear understanding of what are physical changes, let us look at chemical changes and how do we represent these chemical changes as chemistry students.
Right.
We need to understand chemical changes a little better. Let us take up a simple activity to understand the chemical change.
Right.
Ma'am, let's burn magnesium ribbon, ma'am. Can we burn it at room temperature, ma'am?
No, you cannot burn it at room temperature. It is not a metal that will burn at room temperature like sodium. You need to burn the magnesium ribbon. It needs a minimum amount of activation energy to start burning. When we break magnesium ribbon into smaller pieces, it is a physical change. That is what we did earlier. It remains a part of this. That is all. There is nothing new that has happened. Whereas now, I am going to try to burn this magnesium ribbon. I have scrubbed this magnesium ribbon with sandpaper earlier. Why did I scrub it with sandpaper earlier? I saw a white coating on the magnesium ribbon. I tried burning that before I could come to the class. I found that it did not burn easily when there was a coating. We will look at why it did not burn easily a little later. But I did scrub to remove the coating on it and I am heating this magnesium ribbon.
Ma'am, what is the difference between a Bunsen flame and a flame from the spirit lamp? I can notice the color difference.
Right.
This is orange flame, whereas the Bunsen burner, like our LPG gas, gives a blue flame. And the blue flame gives higher calorific value.
True.
And this, there is a lot of soot that is going to be formed. So it's undergoing incomplete combustion.
Very true.
And the fuel that we are using here is
liquid fuel.
Yeah, liquid fuel, ethanol basically, spirit as we call it. Hence the name spirit lamp.
True.
And in Bunsen burner, we use liquefied petroleum gas. And the flame there is going to be blue in color, which is the most high energy part of a flame. Whereas this is not. Ma'am, I'm wondering, is it because of that this is taking a lot of time?
Definitely. When a fuel burns completely with a clean blue flame, it releases a large amount of energy. So it is easier to burn on a blue flame rather than on a sooty yellow flame. And my dear children, it is always better to use a gaseous fuel than a liquid fuel. Though it is liquefied petroleum gas, at a pressure when it comes out, it gets converted into gas and it is the gas that burns. Gas is burned with a clean blue flame. When I say a clean blue flame, it does not pollute the atmosphere. No unburned carbon particles are released into the atmosphere when you burn a gaseous fuel, whereas when you burn liquid fuels like kerosene, petrol, ethanol, etc., many a times they do not burn completely and they burn with a sooty yellow flame. The amount of energy that is released is less, so is the amount of pollution that it causes is also more. So it is better we avoid liquid fuels and move on to gaseous fuels. That is another part for this lesson.
Ma'am, even gaseous, ma'am, we can see a formation of a white solid, but then we are expecting it to burn with a dazzling white flame.
Correct.
That the identification of the formation of oxide is by a dazzling white flame. Yes.
Yes. Now I am sure all of you are able to see the dazzling white flame. Magnesium burns with a dazzling white flame. And
Ma'am, can we
see?
put it off?
Yes, please put it off. Please put off the Bunsen burner first.
Okay, ma'am.
Yes.
I put off the Bunsen burner by cutting off the oxygen supply. Now you can see the formation of a white solid, which is a combination of magnesium and oxygen.
Ma'am, whenever something burns,
1 minute. 1 minute. Yes. Okay. Continue.
whenever something burns in air, it is combination with oxygen.
Ma'am, anything which combines with oxygen can also be called combustion, ma'am.
When it happens at high temperature, it can be called combustion.
And ma'am, when do we differentiate between combustion reaction and then exothermic reaction, ma'am?
Most of the combustion reactions are exothermic
Exothermic.
reactions because they release heat energy.
Yes,
The
ma'am.
energy that is released is more than the energy that we supply for the reaction to proceed.
And
So
can we
they are
call those
exothermic
Yes, ma'am.
reactions.
Sorry, ma'am, but can we call those substances fuels then?
Not all could be fuels. Fuels should have an optimum calorific value and its availability should be in abundance for us to use it as fuel. For example, we don't use magnesium as a fuel
Correct.
because it is also a pollutant and it does not have the other characteristics that a fuel should have.
Correct.
It should have optimum calorific value, it should have optimum ignition temperature, and it should burn continuously for a period of time so that it can be used as a fuel. So a fuel does require other characteristics
Yes.
also.
But burning of a fuel also is classified as a combustion reaction
Very true.
and exothermic reaction.
True.
Ma'am, shall we translate what happened here in the worded form?
Yes, definitely.
Padma ma'am, the change that we just saw, chemical change that we just saw, can we translate it on the board in the form of an equation?
Please, ma'am, we can do it.
So what we are writing now is magnesium combining with oxygen becomes very simple when we write a plus sign. So this part becomes the reactant part, indicating the formation of magnesium oxide. The white color solid that we obtained is magnesium oxide, and this part is the reactant part. The reactant, here there are two reactant, hence reactants, and here we have only one product, so I would write a product here. But ma'am, isn't it very cumbersome to write in word, the reaction in words, when we have a language for chemistry? So
Yes,
can we
definitely.
translate this into an equation?
With symbols and
With
formulae.
with symbols and formulae. So I would write magnesium with the symbol Mg, which is a metallic solid.
Right.
So it becomes imperative that I write that the state it is present in combining with molecular oxygen, which we also call dioxygen, which is in the gaseous phase. Ma'am, do you think it is necessary we write the states as a subscript for all the reactants and products?
It is better we write as much as possible because it gives us more information about the reactants and products. It lets us know as to what state they are in, how we should take them for the reaction to proceed. So it is better we mention them.
Yes. Ma'am, also since you heated the magnesium ribbon, little extra energy as you mentioned was supplied to magnesium ribbon for the reaction to happen. I have written the delta symbol here indicating that we heated for the reaction to happen. So we have a chemical reaction in front of us where magnesium metal combines with oxygen, giving magnesium oxide, like ma'am said, Madhva ma'am, like you said, it's a combination reaction also where two elements here have combined to form a compound, magnesium oxide. This is also in the form of solid. Ma'am, is there anything about magnesium oxide that we can identify about its characteristic? Anything that we can do and identify?
Yes, ma'am. We can find out whether this oxide is acidic or basic. We can dissolve this in water. There is water there. We can dissolve this in water and check whether it is.
You would want to take it in a test tube, or that is fine?
This is fine. And I would like to test. I have added water to this and I have made a solution of magnesium oxide. It's not completely soluble in water. I'll take the soluble part of it and test it with a litmus paper. Magnesium being a metal, its oxide, I presume, should be basic in nature. Bases turn red litmus blue.
We don't have a litmus paper, ma'am.
So we'll do with methyl orange?
Yes, ma'am. We'll do it with an indicator.
I think we have
Litmus, ma'am.
We'll try with
both
both
the litmus.
litmus and methyl orange. First, let me do it with methyl orange.
Okay, ma'am. Ma'am, we are doing it with methyl orange. Indian country.
We'll do it with methyl orange. I'll add a drop of methyl orange to this magnesium oxide solution. I want all of you to observe the color of magnesium oxide before I add methyl orange. Observe this. This is methyl orange. Observe the color of methyl orange. I am going to add a drop of methyl orange to this magnesium oxide solution. What did you observe, children? What did you observe, Radha ma'am?
Ma'am, it's changed color. From colorless, it's become orange.
Become orange? Or it has changed yellow?
It's changing to yellow, ma'am. From orange, it is changing to yellow.
This is orange and this is yellow.
Yes.
So what do we decide from this? Bases turn yellow?
Yes.
When we add methyl orange to it. So magnesium oxide is basic in nature.
Ma'am, there are some oxides, metal oxides, which are not basic oxides.
Correct.
There are some.
There are some.
Probably
like aluminum oxide, zinc
Yes,
oxide,
zinc
which we will learn a little later. Most of the metallic oxides are basic in nature. However, there are a few metallic oxides which are amphoteric in nature. We will learn about amphoteric oxides a little later.
Yes, we'll do that, ma'am. Now, ma'am, looking at this equation, if I look at this equation, it looks a form which is simpler than what I've written here. But then there's something else missing here also. According to law of conservation of mass, matter can neither be created nor can it be destroyed. So the mass of the matter on the left hand side, on the reactant side, should be equal to the mass of the products on the right hand side. Ma'am, it doesn't look like it's happening here.
Yes, it is very obvious that it isn't happening because I find one atom of magnesium and two atoms of oxygen reacting, whereas on the product side, the product has NGO.
Yes, ma'am.
I find here it is O2, molecule of oxygen, whereas I find only O. I wonder as to what happened to another oxygen that
Yes,
was
ma'am.
the reactants.
Ma'am, Padma ma'am, would it make more sense if I say a mole of magnesium reacts with the mole of oxygen to give a mole of magnesium oxide? So, like you very clearly pointed out, the oxygen part is not balanced.
Correct.
The oxygen part on the reactant side is not equal to the oxygen part on the product side. Ma'am, this clearly indicates that the law of conservation of mass is not followed, and we understand for any chemical change, law of conservation of mass has to be followed. Ma'am, there are some reactions in which law of conservation of mass is not followed.
They are called nuclear reactions. In nuclear reactions, an entirely new element is formed because the nucleus of the element gets broken down, new elements are formed. Whereas in a chemical reaction, the nucleus is not involved at all. It is only the electrons, the valence electrons, that are involved in a chemical reaction. So there is no change in mass when a chemical reaction takes place.
Yes, ma'am. So, we could go by balancing this equation. We need to balance. We need to understand, to go according to the law of conservation of mass, we need to balance the oxygen. Ma'am, would it be appropriate if I write a 2 here in order to balance the oxygen?
Yes, it will.
That would result in the magnesium increasing. Increase in magnesium can be compensated by writing a 2 here. This is a simple trial and error method. This is a method where we just check out that part which is on the side which is less and increase it on the side where we need to compensate. This is a simple reaction to balance. Later on, we'll take up some complex reactions which we can try to balance.
I still have a doubt.
Yes, ma'am.
Why make it 2 here and 2 there? I just put it as MgO2.
Ma'am, we hope to remember, I'm sure all of us remember, we cannot change the formula of the compound.
Why, ma'am?
Ma'am, formula is formed by a definite proportion by mass. So,
Correct. We learned that also in class 9. Law of constant proportion.
so we cannot change the formula of the compound.
Yes.
Hence, we need to ensure that we balance by maintaining the integrity of the formula. This is a balanced reaction. Ma'am,
So I want you children to recollect law of constant proportion, which states that elements combine in simple whole number ratio, fixed simple whole number ratio to form compounds. You cannot alter the formula to balance the equation.
correct. So we keep that in mind. Formula should not be altered to our convenience. We need to balance it with keeping the formula intact. That's what we have got a simple combination reaction here. Shall we do another activity where we have another reaction where zinc reacts with dilute sulfuric acid?
Yes,
Another chemical change. Here we had a metal reacting with a gas. Let's have a metal reacting with an aqueous solution of sulfuric acid. Right.
This is called a zinc granule. Can you see the color, children? It is grey in color, it has a metallic cluster, it is a solid. I am going to allow the zinc granule to react with dilute sulfuric acid. I have added dilute sulfuric acid. Look at dilute sulfuric acid. This is a colorless liquid. I am adding a few drops of dilute sulfuric acid to this zinc granule. I am sure all of you know what to observe. Just look at what is happening on the surface of zinc granules.
Yes, I can see evolution of a gas, ma'am. I can see bubbles coming out from the surface of the zinc granules.
Right. Excellent, Radha ma'am. Actually, what you observe, you see bubbles on the surface of zinc granules. And what do we infer when we see bubbles on the surface? We infer that a gas is evolving. Can you smell the gas to see whether it has any characteristic smell?
No, ma'am, it doesn't have. It doesn't have a characteristic color also. I
Right.
can't see it. I can just see it when it's inside the liquid. I can see the effervescence kind of bubbles, but I'm not able to detect any smell or see any color, notice any color. But then there is a chemical change that is happening.
Very true. So, a colorless, odorless gas is evolved. A colorless, odorless gas is evolved when zinc reacts with dilute sulfuric acid. What is the gas that is evolved when zinc reacts with dilute sulfuric acid? My dear children, if I allow it to react for some more time, as more and more hydrogen gets attached to the surface of the zinc granule that is present, zinc will also start floating. It will be a sight to see it floating, but we will wait for some time. We will look at how I inferred that it was hydrogen from the equation. Of course, there is a test for hydrogen which we will do later. First, we will look at it from the equation.
Yes, ma'am. So shall we translate this chemical change in the form of an equation?
First, we will write a word equation. When we represent it in terms of reactants and products by writing the names, we call it a word equation.
Right.
So, we will write a word equation, then a skeletal chemical equation, and then we will balance the equation.
We'll do that, ma'am. Let's write the word equation. So, zinc, solid, since you took a solid,
Right.
dilute, because we took dilute sulfuric acid. Ma'am, does it make a difference when we say dilute and the concentrated sulfuric acid?
Definitely. It makes a lot of difference.
Because concentrated sulfuric acid is an oxidizing agent as well.
Right.
So we shouldn't be taking concentrated H2SO4 or sulfuric acid here. Oh, sorry, cut sir. Word and lamb. Sir,
Yeah, zinc plus zinc went to Kamchana.
zinc plus
No, that's okay.
zinc plus that. So one second, sir.
Yeah.
Ma'am, let's translate the reaction that you just did in the form of a worded equation. Zinc plus dilute sulfuric acid So I have written, ma'am, I can write the products only if I know the formulae of this. So let me parallelly write the formulae also.
Right.
We also know sulfuric acid as hydrogen sulfate. So keeping that in mind, I write the symbol of zinc plus dilute hydrogen sulfate, which is commonly called as sulfuric acid. So, ma'am, would it also be meaningful instead of writing dilute, I could write aqueous here?
That would make better sense. So it is easier to represent in an equation.
Yes, it's easier to represent and it makes more sense if we write the dilute under the reactant and mention an aqueous here. Meaning that this is mixed with water. Now let us predict the products. Now we have a metal reacting with an acid. We have learned in class 9 that when a metal reacts with dilute mineral acid, there is something displaced, which we also saw when ma'am, it's already also happening. So there is something which is getting displaced. What is that which could be displaced? It's a metal, we have hydrogen and we have a radical sulfate. What is that could be displaced from this? Obviously, it's going to be hydrogen gas. So I predict the product H2, and we know hydrogen gas in elemental form is written as dihydrogen. Like we did for oxygen, O2, we need to write it as H2 and not as H. So having written that, now we need to write whatever is remaining, which would complete the equation. So we have zinc and a sulfate. I'll complete this worded equation. So we get zinc sulfate plus hydrogen gas. Now we also write hydrogen gas with an arrowhead pointing upwards. Correct. Completing the equation. And also, ma'am, I am sure all of us will remember that S is capital and O is also capital. We need to remember these are two different elements forming a radical. Z is capital whereas N is small. Many of us forget it and we end up writing either caps throughout or either a small letter throughout. So S and O are capital, Z is capital, N is small letter. Ma'am, is this reaction okay?
Yes, ma'am.
Is it according to the law of conservation of mass?
I think it is. The number of atoms of each kind on either side are the same. So it obeys the law of conservation of mass.
Yes, ma'am. So can we call this as a self-balanced equation?
Yes.
So this is a self-balanced equation. Self-balanced equations are those which are already balanced on its own. We don't have to try to balance them. So we have another chemical change here represented. Reaction of zinc with dilute sulfuric acid. This is a self-balanced equation. Ma'am, shall we take up balancing of a complex reaction in the next session?
Yes, we'll do that.
We'll do that, ma'am.
Namaste.
Namaste.